Thank you very much. First of all, let me thank organizing committee, especially area, to postpone this activity after COVID time interval. And I'm almost newbie in the community of tribology. It was 2017 that I was here in tribology conference. I would like to thank the organizing committee of that conference as well. I will try to talk about the friction in self-assembled structure. Let me say something about my group in University of Tehran. We are working on mostly on nanoscale transport as well as mass transport in low-dimensional structures, as well as modeling materials at the interface, more specifically two-dimensional materials. We have also collaboration with the experimental group on granular materials as well, and I will let you show at the end of my talk. I would take the opportunity to talk about two of our ongoing projects that we are working on. One is a nanoscale self-assembled structure at interface that mostly might be interesting for audience here, and the second is the structure and rheology of ordered structure in granular material. It is not difficult to talk about the importance of self-assembled structure, and we had several outstanding talks on this kind of material. I show a few samples here. You see that for trapping a self-assembled structure on top of graphene and so on, it is difficult to have an island localized in a specific region. We thought that it is possible to think about an allotrope of carbon who called graphene. You see the structure here. It is graphene 1, 2, 3. There is a aromatic chain and triple carbon atom bonds here. By increasing the number of triple bonds, by increasing the number of atoms in this structure, it is possible to have a more irregular pattern with different lattice space, and this these structures could help us to have almost a well-designed pattern to self-assemble a specific two-dimensional structure. We tried with C60 fullerene, but it is possible to consider other nanoparticles. I should say something about the structure. We have a two-dimensional structure. There is sp bond and sp2 bond in this structure. If we take into account the energy landscape of a fullerene on top of this structure, you see that a regular pattern, but the lattice spacing increased by the number of atoms in triangle structure that I showed here. We take this n as the parameter that is possible to change, and it is not the case just for a pattern. The pattern is high sensitive with respect to the height, the distance between the C60 and graphene, and you see that the pattern can be changed with height, different distance between the graphene and here you can have a movie on the diffusion of one C60 on top of these 5 structure. You see that we have kind of diffusive structure here. And by increasing the number of atom carbons, you see that the type of movement from continuous changing into hopping. And here you see that a trap region, and it led to have more localized carbon. And in this case, we could use this diffusion feature to have a more specific assembled structure. You see that the time intervals that one C60 spend in two structure in two position in this structure. We measure the diffusion coefficient. You see that the diffusion coefficient monotonically decreased by the number of atoms in this number of carbon atoms in these structures. And what was more interesting for us was the collective behavior of C60s on top of these two-dimensional structure. You see that with the small lattice size, we have kind of easy movement for island, and the island can find each other and create a almost large island. But on the other systems, the trap is too strong, and the structure could not be extended to have a very large lattice size. More interestingly, it was a feature that we observed. If you look into the graphene tree structure, we have bilayer rather than monolayer structure. For this case, graphene 3 and graphene 4, for both cases, instead of creating monolayered structure, it is bilayer structure, since 160 is not going to attach to the boundary of the structure. It is more favorable for one C60 to jump on top of the first layer and create bilayer structure. It might be more interestingly for a specific application. How much I have time? Okay. This is the reason why we were interested in this kind of a structure. It might be possible to use these structure on top of substrate. What we carried out was a freestanding membrane, but it is possible to simulate them on top of substrate, and it is more than welcome for any comment on this project, as well as experimental group who might be interested in. Let me take the opportunity to talk about another problem that we are working on. The length scale is completely different, but there are some similarities between two problems. If we consider a monodisperse granular material on top of an inclined surface, and if we consider rough and smooth surfaces, the rheology of granular material will be completely different. Here you see that if we have a smooth substrate and we add a little moisture in a given granular system, it is possible to have at first a shear band at top of the system, which means that the velocity profile at the top of the system is completely the same, and the rest is almost a monotonic increase in velocity profile of system. What made us more interested in this problem was ordering, disordering, transition during the rheology, during the in dynamics of the system. Here you have a small video on what is going on dry system. We started to pour granular material on top of a smooth surface, and due to gravity, the system tried to move toward right, and you see that after a specific time, ordering appears in the system. It is starting, yes, completely developed the rheology of system, and in this case we have two-dimensional FCC layers on top of each other, and in this case there is a very small friction between layer, and due to fluctuation of particles, suddenly a fluctuation increase the disorder in the system, and system moves to the disordered structure. This pattern continuously appears and disappears. For this case, we studied the structure. We actually it was studied before for dry systems. We developed lights code to simulate granular material for wet as well, and by this package we compared the structures in dry and wet granular material. You see that here we have almost complete form of crystallization in dry systems for 23 and 25 degree of the inclined plane, but for the almost same cases for wet system, there is no crystallization, and almost polycrystalline structure appears on top of the system. The same story is available for the other structures. Here you see that we simulated a specific spherical tumbler containing wet, the left side, and dry, the right system. Interesting result that could be related to the tribology here is the velocity profile of these two different systems for having more intuitive picture. Here you see that the velocity profile of the structure, these two structures, from this Z point of view. And you see that for the wet system, we have complete velocity developed inside the system, but for the dry one, there is a very a small and narrow layer of moving material, and the rest is somehow the velocity not developed inside the system. Let me thank my collaborator for the rheology part. My student Halime Mustafa Morteza was dealing with, my colleague Reza and Martin. And for the self-assembly problem, I had collaboration with my friends Masume Arman and my student Morteza and my friend Reza. I may conclude here. Thank you very much for your attention.
Thank you. Thank you very much, Mehdi. Questions?
Thanks for your talk, Mehdi. I have a question about the granular materials. Is the size of this particles important, or its scales actually with the size? Every property scales with the size or not in your simulation?
It is not a size-dependent matter case. It is possible to have the same, but when you are mentioning about the size, we have energy dissipation in the system when two wet granular material dissociated. This energy could be comparable with the amount of gravitational energy in the size of a granule.
Yeah, thank you. We've seen very nice results. Perhaps you could give us a little bit of the ingredients that you use. What kind of, say, forces do you have for those granular materials? What's the force field for the C60 and other carbon structures?
For the case of granular one, we have Hertzian model, the well-known, and we have also friction between the granules. On top of them, we add an adhesion, very simple one, a constant force after the first touch of two particles, a constant force appears, and after a given distance dissociates. This was the case for the granular one. For the other case, it is all simulation has been carried out with lamps and Aribo potential for interaction between atoms. All structures are stable with this force field.
I have a question myself about the C60 on the n equals to 3 graphene.
Yes.
I guess the formation of a double layer must have to do, I don't know if the guess is correct, but it must have to do with the fact that in that case, part of the flake of C60 has nothing underneath, right? So those
yes.
atoms, those molecules that have nothing underneath, they better bind somebody else, right? So they form a double layer.
Exactly.
If you had a compact plane, it might be more difficult to have.
Exactly.
More questions? In that case, we're done. Thank you very much.
Thank you very much.